Microsoft and Quantinuum have just made a huge leap forward in the world of quantum computing with the creation of a logical qubit. This isn't just another tech announcement, it's a development that could reshape industries like materials, science, drug discovery, and artificial intelligence. But what exactly is a logical qubit, and why should we care? Well, that's exactly what I'm going to explain in this video. So think of quantum computers as the supercharged version of the computers we use today. Instead of using bits that are either 0 or 1, they use qubits, which can be both at the same time. This allows them to process massive amounts of data incredibly fast. However, qubits are notoriously delicate and prone to errors, which has been a major hurdle in making quantum computing reliable. This is where logical qubits come into play. By combining several physical qubits, Microsoft and Quantinuum have created a more stable and reliable version. This means fewer errors and more accurate calculations, which is crucial for solving complex problems. Imagine being able to simulate new drugs or materials with precision that was previously impossible. So initially, the teams managed to create 4 logical qubits using 30 physical qubits, achieving an error rate 800 times lower than that of physical qubits alone. This was a remarkable feat, but they didn't stop there. Through continued research and development, they expanded their work to create 12 logical qubits using 56 physical qubits, achieving a fidelity of 99.8% for 2-qubit operations. This level of precision is crucial for tackling complex problems in fields like drug discovery, climate modeling, and secure communication. A key aspect of this breakthrough is the demonstration of entanglement among logical qubits. Entanglement is a unique property of quantum physics where the state of one qubit can instantly affect another, regardless of distance. This was achieved using a complex arrangement known as a Greenberger-Horn-Zeilinger state, which involves multiple qubits being entangled simultaneously. The low error rate in these experiments brings us closer to fault-tolerant quantum computing, where systems can function correctly even if some qubits make errors. The process started with identifying the active space of a catalyst, which is the part of the catalyst responsible for its chemical reactions. To do this, scientists used high-performance computing simulations. HPC allows computers to process large amounts of data very quickly, which helps scientists understand complex systems like catalysts. After figuring out the active space, they used logical qubits to simulate the quantum behavior of this active space. Quantum behavior is how particles like atoms and molecules behave at the smallest scale, and it can be very hard to predict using regular computers. This is where quantum computers come in handy because they are better at handling these kinds of calculations. So once they ran the quantum simulations, they got measurement results that helped them understand how the catalyst behaves, but they didn't stop there. These measurement results were then fed into an artificial intelligence model. The AI model used this data to learn and improve its understanding of the system. Eventually, the AI was able to provide a very accurate estimate of the ground state energy of the catalyst. The ground state energy is the lowest possible energy that the system can have, which is important to know for understanding how stable or reactive the catalyst might be. This entire process, starting from HPC simulations, using quantum computing to simulate the catalyst's behavior, and then training an AI model to give accurate results, represents a huge breakthrough. It's the first time that quantum computing, HPC, and AI have been combined to solve a scientific problem from start to finish. This achievement shows that quantum technology isn't just theoretical anymore, it can actually be used to tackle real-world scientific challenges. The current results of this study don't yet show what's called a full scientific quantum advantage. Quantum advantage is when quantum computers can solve problems that classical or regular computers simply can't handle. In other words, we haven't quite reached the point where quantum computers can completely outdo classical computers in all areas. However, these results do show that quantum systems have the potential to outperform classical methods in specific situations. In this study, a hybrid approach was used. This means the scientists combined both quantum computing and classical computing methods. The combination of the two helps boost the overall performance. While quantum computers still have limitations, especially since they are new and developing, this hybrid method shows how quantum technology can already be useful in certain areas. One of those areas is chemical computations. Classical computers are very good at solving many types of problems, but they can struggle with complex chemical systems, especially when it comes to understanding how molecules behave at the quantum level, the smallest scale. These types of problems require an enormous amount of computing power, and classical computers can only go so far before they hit a wall. This is where quantum computing comes in. In this study, using quantum computers made the chemical computations more accurate, especially for problems that are very difficult for classical computers. For example, quantum systems can model the behavior of molecules in more detail than classical systems, helping scientists predict chemical reactions or discover new materials more precisely. While quantum computers aren't yet fully surpassing classical computers in all tasks, This study highlights how they can complement classical methods. By enhancing the accuracy of tough computations, quantum technology is already showing its value, and it's likely that as these systems improve, they will become even more powerful and useful. Microsoft has big plans for its quantum computing platform called Azure Quantum. The company says it is committed to improving and expanding this platform to support different types of qubits, which are the building blocks of quantum computers. Two types of qubits Microsoft is focusing on are neutral atom qubits and topological qubits. Neutral atom qubits are qubits made from neutral atoms, which are atoms that don't carry any electric charge. These qubits are controlled by using lasers to arrange and manipulate them. One of the benefits of neutral atom qubits is that they can be packed closely together, which makes them very efficient for building large quantum systems. They are considered highly promising for scaling up quantum computers, meaning we could eventually build much bigger quantum computers with more processing power. Topological qubits are another type that Microsoft is interested in. These qubits are different because they are designed to be more stable and less prone to errors. The idea behind topological qubits is that they store information in a special way that protects it from being easily disturbed by outside factors. This could make topological qubits more reliable for quantum computing. However, creating topological qubits is still a major scientific challenge, and Microsoft is investing in research to make them a reality. By integrating these diverse types of qubits into its Azure Quantum platform, Microsoft hopes to create quantum computers that are more reliable and can scale up to handle much larger problems. Reliability is essential because quantum computers need to perform operations without making too many errors. Scalability is also important because the more qubits a quantum computer can handle, the more complex calculations it can solve. Microsoft believes that quantum computing will eventually become powerful enough to tackle some of the world's biggest challenges. This includes things like discovering new medicines, developing cleaner energy sources, solving complex climate problems, and even creating more secure communication systems. But to get there, quantum computers need to become more practical and scalable, and this is exactly what Microsoft is working toward with its Azure Quantum platform. The collaboration between Microsoft and Quantinuum is a testament to the power of combining expertise from different fields. Microsoft brings its extensive experience in software development and cloud computing, while Quantinuum contributes its cutting-edge research in quantum hardware. This partnership is not just about creating logical qubits. It's about building a robust ecosystem that supports the entire quantum computing process, from hardware to software. One of the most fascinating aspects of this collaboration is the use of ion trap technology. Ion traps are devices that use electric fields to hold charged particles, or ions, in place. This technology is crucial for creating stable qubits, as it allows for precise control over the quantum states of the ions. By integrating ion trap technology with Microsoft's qubit virtualization system, the teams have been able to achieve unprecedented levels of stability and accuracy in their logical qubits. If you've made it this far into the video, let me know what you think in the comments below. For more interesting topics, make sure you subscribe to the channel and watch all the recently uploaded videos. Thanks for watching.